So the next thing we'll be discussing how CPU scheduling is done and what are the two important categories of scheduling. So basically we have discussed about short-term scheduler. So short-term scheduler is the one which decides like which process should be given the CPU access, which process should be allocated with the processor. So that decision will be made by the short-term scheduler. So basically short-term scheduler is a queue. Basically short-term scheduler is a queue. So it contains list of process and these process will be assigned to the processor in some order. So, so maybe it may contain n number of process P1, P2, P3, P4, so on and so forth. Like that, it can have any number of process. Okay, and and short-term scheduler is the one which decides who should be given processor next. Okay, so this queue can be of different type. Okay, it is not that this queue will be always a FIFO queue. FIFO in the sense first in first out. So it doesn't mean that always the process, always the job or the process uh, which is in the end of the queue, or which is in the front end of the queue. So this is the front end of the queue. Okay, and this is the rear end of the queue. Okay, so this is the rear end. So it is not that always the process which is in the front end of the queue will get the processor. No, it can be of different. The queue need not be of only FIFO style. It can be of different other style also. Maybe it may be a priority queue. Okay, it may be. It is not that it should be only a FIFO queue. It may be a priority queue. In a priority queue, the process with the highest priority will get the processor first. Okay, maybe this process may have a priority of 2. Okay, this may have 3, whereas this may have 8. Process 3 P3 has a priority of 8, and this may have 7. So in this case, process 8 may get the processor first. Okay, so that's the point here. The queue need not be a FIFO queue. It can be of some other type also, right? Okay, and then we'll be discussing normally when a process will when the CPU will context switch. Okay, so we are discussing CPU scheduling. So when a CPU will context switch, so CPU will perform context switch under 4 conditions. The first condition is CPU will perform context switch under 4 situations. The first situation is if the process is moving from running state to waiting state. If any process is moving from running state to waiting state, that it is running, it is now moving to a waiting state because of an IO operation. Okay, so now the context switch will happen. So this is the first case, that is the process is moving from running to waiting state. During that time context switch will take place. Okay, because now the CPU should bring in new process. And the second situation is when a process is moving from running state to ready state. When a process is moving from running state to ready state, because every process has a time slice. Okay, a process will have a time slice when the CPU is executing. For each process, it will give a time slice. Process 1 will execute for 5 milliseconds, 2 will execute for 6 milliseconds, like that. So once the time slice is over, the running process will be moved into ready queue. Okay, and some other process will be brought into the, some other process will be allocated to the processor. So during that time also context switch happens. That is when a process moves from running state to ready state. Okay. The third situation is when a process moves from waiting state to ready state. When a process moves from waiting state to ready state. Okay. So in the third case also context switch may happen. When a process is moving from waiting state to ready state. Okay. And the fourth state is situation is when a process terminates. The process is currently executing, but it suddenly terminates. It is completed. Then the processor is idle, so it has to take a new process. So during these 4 situations, context switch will happen. Okay. when a process moves from ready to, when a process moves from running to waiting state, and when a process moves from running to ready state, and when a process moves from waiting to ready state, and when a process terminates. So during these situations, context switch will takes place. Okay, and there are two types of scheduling algorithms we'll be discussing. Many scheduling algorithms we'll be discussing, but broadly these scheduling algorithms can be classified into two categories. One is called as preemptive scheduling. The other is called as non-preemptive scheduling. The first is called as preemptive scheduling. The other one is called as non-preemptive scheduling. Okay. So what is meant by preemptive scheduling? So preemptive means once the processor is allocated to the process, if the operating system wants to take away the processor CPU from that process, it can take away. So that is called as, that is the meaning of preemptive. Preemptive means after allocating CPU to a particular process, if the operating system wants to take away the CPU later, it can take away. Okay. So 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 in a preemptive scheduling, if a process is allocated to a particular CPU, and later after some time CPU, if the operating system feels that now I want to take the processor out of that process and I want to give the CPU to some other process, then the operating system is free to do that. Okay, so such scheduling is called as preemptive scheduling. Whereas in a non-preemptive scheduling, once the process is allocated to the CPU, once the process is allocated to the CPU, say a particular process P1, it is allocated to the CPU, then the CPU cannot be taken away from this process. Then the CPU cannot be taken away from this process until the process either terminates. How long it cannot be taken away? In the sense, until the process either terminates or it went to an IO wait, or it went to an IO wait state, because it want to perform an IO operation. So it went to an IO wait operation. Okay. Until then, the CPU cannot be taken away. So such type of scheduling algorithms are called as non-preemptive scheduling. Okay. I guess you understand. So there are two types of scheduling algorithms available. One is called as preemptive scheduling, the other one is called as non-preemptive scheduling. With preemptive scheduling, once the CPU is allocated to a particular process, the operating system can take away the CPU from the process at any time. Whereas in non-preemptive scheduling, after allocating the CPU to a particular process, the CPU cannot be taken away until the particular process either terminates or it get into an IO wait state. Okay. So here, you can say that uh, case 1 case 1 and case 4 are non-preemptive scheduling. Okay. So that is the processor CPU is switching from, the context switch is happening only when the process is moving from running to wait state. Okay, that is the context switch can happen only in these two situations. That is, the CPU, the process is moving either from running state to IO wait state, or the process itself terminates. So these two are examples of non-preemptive scheduling. These two are examples of non-preemptive scheduling. Okay. So this number one, the point 1 and point 4, these are the cases of non-preemptive scheduling. Okay. So this is what preemptive and non-preemptive means. So all other cases of scheduling is preemptive. Okay. But if you take in today's situation, most of the operating system, it uses preemptive scheduling. The original version of Windows 3.1, it uses non-preemptive scheduling. But after that, from Windows 95 onwards, it is using, Windows operating system is using preemptive scheduling. So as of the current scenario, if you take any typical operating system, it follows preemptive scheduling. But there are certain issues with preemptive scheduling. So basically, what is preemptive scheduling? Preemptive scheduling means once the once the process is allocated to the the CPU cannot be taken away by the operating system until and otherwise the process get into a wait state or it terminates. Okay. So whereas in a preemptive scheduling, the operating system can take away the CPU at any time from the process. Okay, but there are certain issues in that. Let us try to understand what are the issues. The first issue is with the issue of shared data. The first issue is with the issue of shared data. So this problem is called as race condition. This problem is called as race condition. So what do you mean by race condition? So what is meant by race condition? So race condition means, so the first problem is with the shared data. So this can also be called as race condition. So what is how we define race condition? Race condition in the sense, assume that currently in the ready queue there is only one process P2 is waiting. P2 is waiting in the ready queue, and CPU is allocated to a particular process called as P1. Okay, CPU is currently executing a particular process, and that process is called as P1. Okay, that process is called as P1. And let us say that P1 and P2 are using a shared memory. That is, P1 can also access this, and P2 can also access this shared memory when it got the CPU. Currently, it is not accessing because currently it is in the uh, uh, ready queue. Okay, it is in the ready queue waiting for the CPU. And this shared memory is this shared content is shared by both P1 and P2. Okay. Now it is a preemptive scheduling. Preemptive scheduling means operating system can take the CPU away from the process at any time. So let us assume there is a variable x, and let us assume that this particular process is currently updating this x. It is updating this x, and the updation is not completed. It is in the process of updating the x, and by that time operating system preempts. By that time operating system preempts. Okay, preempts means what? It takes away the CPU from the process P1. It takes away the CPU from the process P1. So this write operation is incomplete. Whatever P1 is performing the write operation, now the CPU was taken away. So and it has not completed that particular task. So this is an incomplete and inconsistent task. So this becomes an incomplete and a inconsistent task. Okay. So later assume that the processor was given to P2. The processor was taken away from P1 and it is now given to P2, and P1 is in the waiting state. Now P2 is accessing this shared memory and it tries to read the x, and it finds that the value of x is inconsistent. The value of x is inconsistent. That is, it is not in the correct format, or it is corrupted. Okay, so this issue is called as race condition. So this issue is called as race condition. So how can we put up race condition? So race condition in the sense, if two processes were using a shared resource, and if one of the process is currently writing into the shared resource, and during that time if context switch happens and if the write is incomplete, and when the other process comes and checks that particular shared memory, it will find the data to be inconsistent. So this situation is called as race condition. How to deal with race condition or how to overcome this problem, that we will be discussing later. But this issue may happen with respect to preemptive scheduling. Okay. Similarly, there is another problem with preemptive scheduling is, so we know that there are two types of process. One is user process, the other one is kernel process. User process are the one which are created by the user program, and the kernel process are the one which are created by the operating system. Okay, so both user process and kernel process were executed by the CPU, that is the processor, right? Okay, now so we are discussing the issues with non-preemptive, sorry, issues with preemptive scheduling. Now let us assume that CPU is currently executing some kernel process. CPU is currently executing some kernel process. Let us call it as K1. It is CPU is allocated to a kernel process, and the name of the kernel process is K1. And what this process is doing, say it is doing very important task. It is maintaining some data structure, a queue data structure. It is either creating a queue data structure for a particular process, or it is updating that data structure, or it is reinitializing this, some very crucial task it is doing. Let us assume this particular kernel processes, and during that time, say say the operating system context switched. That is the this particular process was removed from the CPU, and CPU is allocated to some other process. Now what happens? Again, this particular crucial operating system task, crucial kernel task is not completed, and this may lead to some chaos. So this may lead to some chaos. Okay. So because, okay, this may lead to some chaos. So this problem also may occur because of preemptive scheduling. Okay. So the problem is when there are two types of process. One is a user process, the other one is a kernel process. If kernel process is doing some important task, and during that time, if the operating system preempts the CPU from that process, then it may lead to a lot of chaos. Okay, so to avoid that, most of the operating systems, what they do in the sense, if if the data structures, if the kernel data structures are inconsistent during an context switch, then during that time they will not perform the context switch. They will wait for that particular system call to complete, and to ensure that the kernel data structure is consistent, and then they will go for context switch. Okay, so this is the second problem with the preemptive scheduling. And the third problem is what happens when an interrupt occurs. Okay, so if the operating system is doing some crucial activity, and during that time there is an interrupt. Okay, say say again, okay, say one of the operating system process is running by the CPU, and it is performing a very important task which is related to an operating system. Okay, so CPU is performing some process. Say let us assume it is a uh, even you can assume it as a kernel process. Let us assume it is a kernel process, not a user process. Okay, so this kernel process, what it is doing, it is performing uh, some crucial task related to the operating system, some crucial task for the operating system it is doing. Okay, and let us assume during that time there is an interrupt. So whenever there is an interrupt, what the CPU should do? CPU should stop it and process the interrupt. But here this is a crucial task, and you cannot uh, stop it. Okay, so this will also may create problem. Or the second case is assume that this particular process, it is doing some task, some important task. Okay, and say that this interrupt also want to access the same memory. This interrupt also want to access the same memory. Okay, so 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 that is this particular interrupt also want to access the same memory. Now if you give access, then this content again it may become inconsistent. Okay, so this is the third problem with preemptive scheduling. So to avoid this, normally this when this type of important OS related activity is going on, so what the process will do in the sense, so when this particular crucial task is being executed, the first statement here it will be to disable interrupt. The first statement here it will be to disable any interrupts. That is during that is no interrupt can occur. Okay, until it is enabled. So the first instruction here will be to disable interrupt. And once all the instructions are executed and the crucial operating system task is completed, then the last instruction here will be enable interrupt. Okay, so this is how we can stop such activity. Okay, But this disable interrupt and enable interrupt, this type of instructions will be executed very rarely. It won't be executed frequently by each and every process. It will be executed only when some high priority or crucial operating system task is being going on. Okay, so these are the typical three problems which can occur with preemptive scheduling. The first is the race condition. The second is when the operating system is running some kernel process, and during that time, if the context switch done, then it may lead to chaos. Okay, and and uh, and the third case is when the operating system, when when some of the, if the CPU is executing some crucial OS activity, and during that time, if there is an interrupt raised, if there is an interrupt raised, then it may lead to inconsistent operation. And to avoid that, whenever an operating system performs a crucial task, the first step is to disable the interrupt, then perform the task. Once the task completes, enable the interrupt, so that during that time it will not be disturbed by the interrupts. Fine. So previously we have discussed that the short-term scheduler is also called as dispatcher, but actually in reality short-term scheduler only decides that who will be the one who will get the next, who will be the one, which process will get the processor next. That decision only will be made by the short-term scheduler. But there is another unit called as dispatcher. There is another hardware unit called as dispatcher. Once the decision is made by the short-term scheduler, like which process should be assigned with the CPU, then the dispatcher is the one. Then the dispatcher is the one which moves the process, from the ready queue to the operating system, to the CPU. Okay, dispatcher is the one which moves the process from the ready queue to the CPU. But which process should be moved, that decision will be taken by the uh, short-term scheduler. Okay, and there is a concept called dispatch latency. It is very crucial. So the dispatch latency, it is basically the time required by the dispatcher to stop one process and start running another process. Okay, it is the time taken by the dispatcher to stop one process and start another process. Okay, so dispatcher should execute at a very faster rate. So now let us discuss the scheduling criteria. What are the various scheduling criteria? So, so, so basically, the CPU scheduling algorithms are measured based on some criteria. So those criteria we'll be discussing here. The first one is CPU utilization. So this is measured in terms of percentage. So how much the CPU is getting utilized. So this, so in theory, the CPU utilization can vary from 0 percentage to 100 percentage. But in practice, it varies from 40 percentage to 90 percentage. When the system is lightly loaded, it will be around 40 percentage. And when the system is heavily loaded with many processes, it will be around 90 percentage. Okay, this is CPU utilization. It's one of the criteria to measure the performance of the scheduling algorithm. The second is throughput. So throughput, basically it defines the throughput is defined as the amount of work done per unit time. Amount of work done per unit time. So here it is defined as the number of processes completed per unit time. So under CPU scheduling, throughput is defined as the number of processes completed per unit time. So if it is a longer process, it may be like number of processes completed per hour. If it is a small processes, then it may be like number of processes completed per second. Okay, so that is the throughput. The third is turnaround time. So turnaround time is the time duration. Turnaround time is the time duration between the submission of the job to the completion of the job. So it is the entire time duration between the completion of the job and submission of the job and completion of the job. Okay, so it includes everything like how long it is in the wait queue, how long it is in the ready queue, how long it is executing, all put together. The entire time duration between the submission of a process and completion of the process is called as turnaround time. Third is waiting time. So waiting time is basically defined as how much time the process is waiting in the wait queue, in the ready queue. Sorry, how much time the process is waiting in the ready queue. So basically it is only the time duration the process is spending in the ready queue. So that time duration alone is called as waiting time. Okay, because see process normally where and all it spends time. It spends time either in executing, that is the process is running, or it spends time waiting for IO when an IO operation is performing, or it spends time in the ready queue. Okay, so this so waiting time basically it includes only the time that is spent by the process in the ready queue. So it is the time that's spent by the process in the ready queue. How long the process stays in the ready queue during its entire lifetime, how long it stays in the ready queue. So this duration of time is called as waiting time. Okay, how much time it is staying in the ready queue. The next is response time. What is response times? So sometimes turnaround time may not be useful in some situations. So turnaround time is basically the time duration between the submission of the job to the completion of the job. Whereas response time is the time duration between the submission of the job and the first response. Submission of the job and the first response from the particular job or process. Okay, say a particular process is you are submitting at time t for execution. Okay, submitting at time t naught, at t naught you are submitting. Okay, say it completes at time t20, it completes at time t20, but it gives the first response at time t4. Okay, at time t4, then the time duration between t0 and t4, so that is what is called as response time. Okay, the time duration between the job or process submission and the first response, that is called as response time. First response means it may ask something, enter your name or enter your age, or some form may pop up, so that you will understand that okay, the job is started executing, but it is not completed, it completes at t20. Okay, so this duration is called as response time. Whereas the entire time duration from t0 to completion time, so this is called as turnaround time. So these are the various criteria by which we measure the performance of the scheduling algorithms. And the objective here is to maximize the CPU utilization, to maximize the throughput, and to minimize the turnaround time, to minimize the waiting time, and to minimize the response time. Okay, so this is the introduction to CPU scheduling. And in the next class, we'll discuss various scheduling algorithms. Okay, we can stop here. Thank you.